Sophia Isaac, and this is my Physics 2212 Experiment 4 for Faraday's Law. So to start, this is a general overview of what I'm going to be talking about, and I'm going to start with the introduction. So the purpose of this experiment is to observe a magnet falling through a conductive tube of aluminum foil and then creating a computational model to compare those values that we took of the measured times. And this is under the assumption that error resistance is negligible. And some of the results that I got was the measured average time falling inside the tube was 2.118 seconds, and the computer code's time was 2.439 seconds. So for some background information, first is Faraday's law, which is that the induced voltage is proportional to the flux, as we see right here in the equation. Then magnetic flux is the magnetic field that's going through an area, so the amount of the magnetic field that's going through the area. And then the Lenz-Rossi induced current creates a magnetic field with opposite direction to the E external, and we see it right here as well in the equation. And then the Biot-Savart law, which we had talked about before in other projects, in other labs, is that the magnetic field is proportional to length of current. So for the procedure, we can see that the system is a magnet that surrounds the aluminum, and the initial conditions is that Vi equals 0. So what we had to do for this project was to mark the north pole of the magnet using the magnetometer app that we had used before, and then hold the tube vertically and position the magnet at the top. We also had to record the magnet falling down the tube, and then record the time when it enters the tube and when it leaves in order to find the amount of time that the magnet was inside of the tube. So we have to repeat this 5 times and then find the average time of all of those trials. And this is the measurements that I got for the tube length, width, radius, dipole moment from a previous lab, and then the bar magnet mass. So these are the results that I got the first time I did it. I got 2.15 seconds, and then this is trial 2, 3, 4, and 5. And then I just did an average value of all these numbers, and I got that the average time that the magnet was inside of the tube was 2.118 seconds. So then for the code, I basically just changed things accordingly based on the starter code. So I changed these measurements that I had mentioned before, the length, the width, and the inner radius. And then I also changed the magnitude of the magnetic dipole moment as well. Then I also started changing the function in order to calculate the dipole, and then in order to calculate the df dt for this. And here we can see also we edit this in order to find the force of gravity as well. And then this is non-editable. This is for the ring current. And then in this other side, we can see that we are calculating the magnitude of the force on the magnet, and we just basically add the previous forces that we had calculated together. Then we also have the F magnetic field and F net, which is the magnetic field plus the force of gravity that we have. And then this is just finding the velocity and then the position of the bar, and then this is just a plot. And this is the results that I got, basically saying that the time in tube in seconds average for this computational model was 2.39 seconds. So for the conclusion, the intensity of the coloring on the tube indicates the magnitude. Red and blue indicate different flows, which is counterclockwise and which is clockwise, and how do you know? So blue corresponds to counterclockwise and red is clockwise, since the induced current flows counterclockwise due to flux, and blue is that. What happens to the dynamics of the system when you flick the magnet around? The current would flow in the opposite direction, but everything else, so like the magnitudes and the values, would remain the same, just opposite directions. And then, how does the total time in the tube compare to the real world system, and how may it be more accurate? So it is almost the same, it is pretty close, but I think in order to make it a little bit more accurate, we should take into account error resistance, since we are saying that it's negligible, but at the same time in real life error resistance does exist. So I think with the computational model, if we add that, it would be more accurate. And then what does the shape of the velocity versus plot tell you about the forces acting on the bar magnet? So the velocity decreases and then reaches a constant value until the end and decreases again. And in that constant value, the acceleration is 0 because the slope of the velocity graph is 0. So possible sources of error are errors due to rounding or math, error when measuring times, or the magnetic fields not taken into account, possibly. And similarities are pretty similar, but as I mentioned before, they're a little bit different due to error resistance, negligence. And then what if the resistivity of the conductor were reduced as close as possible to 0? So the induced current would increase and the magnet would take more time in the tube since it falls slower due to a greater magnetic force. And then consequently, what if there were holes in the tube? How would this affect the ring currents? So what would happen is the holes in the tube would increase the resistance, and it would decrease the induced current, and therefore it would decrease the magnetic force, so making it last less inside the tube and fall faster.